Last lesson, we looked at this idea where uh, now lots of people have had, especially in the other class, this class appears to have just accepted the fact that that this diagram here is an atom and energy levels in an atom, and that I can allow a photon, and we look at single electrons, different energy levels, very discrete energy levels, and single photons going in. It's just a simplified version. Of course, this is not how it happens. There's lots of these things, and there's lots of these things in a metal. So, but let's just look at one transition. A photon comes in. The photon has, what we're saying is this is minus 20 eV and 15 eV. Where is the greater amount of energy in this energy level diagram here? This now a common misconception, and this is part of the issue that I have with the textbook, is that this might be minus 8, minus 0.8. As we go higher in this energy level diagram here, or we go vertically upward, we go from minus 20 eV up to minus 0.8 eV. Now, these are negative energies, which I don't like saying that they're negative energies, but essentially these electrons up here, because we have energy coming into the atom, it excites an electron in the lower energy level, or the ground state, you might say, up to a higher energy state. So this number, this minus 0.8, is actually a higher energy state than this minus 20 eV. Okay? Now, so this is the most excited electron. And we've drawn it traditionally like this. These diagrams are connected in some way. This diagram, though, I keep saying is incorrect. These are energy levels perhaps around the atom, and they have, of course, electrons. These are electron paths, so to speak. It's not how it happens, but we're just going to draw it for simplicity's sake. There's some electrons in these, what we call orbitals. The most energetic electrons are these ones in the outer shells. Call these shells. These are the outer shells. These outer shells correspond to these higher energies. These higher energies are represented by numbers that are smaller and negative than this number down here. But you can see that a free electron has how much energy? At the moment that it becomes free? 0, doesn't it? Yeah, so we're working towards this 0 eV of energy. That would be a free electron. There. But it's not really going anywhere, is it? It can't be going anywhere because it hasn't got any energy. If it hasn't got any energy, then it has no velocity, because that's how we describe these electrons. We say, well, that has 5 eV of energy. That has energy is difficult to define. Energy is kind of the ability to do work. But in this definition, I'd say that the electron has 5 eV of energy. Its speed is related to that. Okay, it's velocity by this K equals half mv squared. So that's how energy and velocity are related. The mass is fixed for an electron, of course. So at 0 eV, it has no energy, no velocity. It's free of the atom, but it's not going anywhere. We have to give it a little bit more to make it go somewhere. Yeah, that's right. It's a good question. Yeah, by having mass, it has energy. By Einstein's famous T-shirt equation. It's on T-shirts now, apparently. Yep. Mass isn't dependent on... Oh, well, it is, yes, when you're talking about relativity. Yes, but we're not going to talk about that. The higher this... well, in fact, the greater the energy, greater the mass. And that's shown here, okay? Energy and mass are related and proportional to each other. But don't worry about that right now, okay? We'll do that later. Now, so here's this. I'm sending in a photon of 5 eV, we said before, and it can jump. It can make this jump to this higher energy level, this higher energy state, which has a smaller number and a negative, minus 15 eV. If I give it, say if I gave it 25, eV of energy, then it can make this jump to here to become free, and it's still got 5 eV in its pocket, and it can fly off at 5 eV, so to speak. It's what we would call, physicists would call, a 5 eV electron. Okay, 5 eV. I don't know what speed that is. You could use this to do the calculation if you'd like. If somebody wants to do that and tell us what 5 eV is in speed. We define this work function as well, and we've done that earlier. Work function of copper is 4.7 eV. Can anybody remember the definition of work function? Yeah, the minimum. That's right. Energy required for the atom to, oh, that doesn't look very good, does it? To release an electron. There's another way to say it as well, which sounds contradictory. It's the energy required. I should do this I should have done this in a different color, shouldn't I? It doesn't matter. Required to remove or release, I'll say release again, release the most energetic electron. Does that sound contradictory? Minimum energy required for the atom to release an electron, but it's also the energy required to release the most energetic electron. Doesn't sound very good, does it? Imagine, we know, we have this idea that this guy, we're going to pick on one of them, and we'll say this one here is the most energetic electron around that atom. Now, that electron there might correspond with this minus 0.8 eV. Can you see the work function based on the energy level diagram? This is a fictitious energy level diagram, but based on this energy level diagram that I've drawn at the top here, the work function of the metal is the minimum energy required to release an electron, which is how much? If I give that atom or that electron 0.8 eV, then it becomes free. That would be the work function of this surface here. Can you see that that's the minimum energy required to release that electron, and it's also the energy required to release the most energetic electron around that atom? It's the same thing. Okay, we'll move on. Remember, the threshold frequency is F sub 0, we've said. The minimum energy, now, this might be an electron. Oh, sorry, this might be a photon. What do I want to say here? Oh, okay, let's say, I'll move down a little bit. We got any space here? No. I'll fit something in here. Imagine I send in a photon with this energy. Exactly the threshold frequency. Okay? That frequency there is related to some substance, isn't it? Usually a metal. Now, when it strikes that metal releases an electron at some speed. Well, it doesn't really, does it? That electron is just merely free. If we hit it at the, let's say that this is an atom, okay, with an electron in its orbit. Threshold frequency, it gives enough energy to this high energy electron here around the atom just to release it from the atom. It's not bound to that atom anymore. It now has 0 eV of energy. Hasn't got any speed, but it's not bound to that atom anymore. If I give it more energy, say if I increase that energy to, I'll just rub this out first, some value F, and F is greater than the threshold frequency. Okay, so greater than the threshold frequency. How much energy is that electron going to have? Yeah, we know that the energy of this photon here is E equals HF, isn't it? Now, but to free that electron, I've got to supply the work function, don't I? I've got to supply a certain amount of energy to make it to 0 eV first, to bring its energy level up to 0 eV, and then whatever's left over is what speed the electron has, or what energy the electron has. So the energy that the electron has then, and I'll draw in a little electron when it comes off, is equal to HF, which is the photons given it. It either does or it doesn't. If it's given that electron any energy at all, it's given it all of it, HF, minus the work function of that metal, whatever is required to bring that electron up to the release state, to the 0 eV state. Okay. Now, I'm repeating myself a little bit because we defined this yesterday. HF minus W. So the maximum kinetic energy that an electron will have is HF minus W, because W is just the most energetic electrons in that atom, isn't it, already? So the maximum energy that you're going to see in any electron emitted from that substance, whatever that metal is always going to be HF minus the work function of the metal. Here we have, we talked yesterday about being able to draw these graphs. The graphs always look the same in either EV or joules. It's fine. Frequency is always measured in hertz. Notice that this formula here, just a reminder, has the same format as y equals mx plus c, m being h, of course. For this one here, HF minus W is actually H on E F minus omega, and that's in EV, and K max is in EV. So if I have my kinetic energy written in EV and my work function written in EV, then the slope of the line is actually H on E. All right. We started this problem yesterday, and we did another problem, didn't we? That one was okay. Stopping potential for electrons emitted from a metal by light of 4 different wavelengths. And what we did was, the wavelengths are no good for this, for calculating Planck's constant. We need frequency. We need frequency in the x-axis. So we converted these 6 by 10 to the 14, 7.1 by 10 to the 14, and so on and so forth. Stopping potential. If I'm drawing a graph with my kinetic energy in electron volts, what is my stopping potential then? Stopping potential there is just the energy in EV that the electrons do have. Because remember, if I have a potential difference in a different color, if I have a potential difference here, so there's an electric field in there, isn't there? Think about that as an electric field. The only reason that we know that there's a field there is because it has effect on charged particles as they move in that field. I fire an electron across that. What it does is it goes up. It almost gets there, turns around and comes back down. comes back to the left, okay? Almost gets there, the electron. It's traversed that whole distance before it's slowed down to zero, basically, hasn't it? If an electron, something with an electron charge is able to traverse a certain distance, if we know what that potential difference is, then we know the energy that that electron has, okay? If that potential difference is 1 volt, 1 volt, and that electron, in being able to traverse right to the other side before it goes to zero, has 1 electron volt of energy. Now, so I can just use these, because I'm drawing my graph in EV, I can just use these stopping potential 0.33, 0.79, 1.49 and 1.82 as my energy in EV, because they convert very easily. 2, 4, 6. Okay, so what I might do is I'll do it in red because it'll be easier to see. I'm going to say that's 0.5, 1, 1.5, 2. So 0, 0.5, 1.0, 1.5, 2.0. Okay, we'll leave it at that. And I have frequencies. 6, 7.1, 8.8, and 9.7. Incidentally, imagine if I had this frequency, just so you can, just in case, because I think I've seen this come up before. Imagine if I had 1.1 by 10 to the 15 hertz as well. How would I put that on here, considering I put 10 to the 14 hertz there? I've said that my frequency is multiplied by 10 to the 14. Yeah, exactly. Exactly. I can actually make that 10 to the 14 and move that decimal place to the right one. And then it becomes an 11. That's right. Exactly. That's fine. But we haven't. We've got 6. So I've got to go up to 10, don't I? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I might be able to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 3, 4, 5. And 10's up there. That's fine. Okay. Now let's draw in our values. For 0.33, we've got a frequency of 6 by 10 to the 14. 0.33 is around here somewhere. That's 0.25, that's 0.33. We can go up to 6, which is there. 0.79 is 7.1. So there's 6, there's 7.1. Up to 0.79 is 0.8, there's 0.78, 7.5. About there, we happy? Tell me if I'm wrong. The next number is 1.49, 8.8. Just under 1.5. There's 8, 5, 6, 7, 8, 9 is about there. Is that right? And last numbers, last coordinates, 1.82, 9.7. 1.82 is up here somewhere, and 9.7 is just under 10. So we might have a there, something like that. Maybe a little bit more left of that. Okay. Then I can draw my graph. I'll draw it from this point here. Now I'm going to extend it under the x-axis. I've got to be careful this doesn't fly up too like that. Oh dear. This isn't going to look very good, but that's okay. Oh yeah, that's all right. Good. Now, I've drawn my graph. That's reasonably good. What they want you to calculate from this graph, and you might have taken these measurements using the stopping voltage and calculating the frequency. You've graphed it. You've taken more data points than 4 4 is a bad idea. And then what they say is, the first question is, how do you find Planck's constant? What do you do? Yeah, that's right. We just do rise over run, don't we? So there's rise, and I'm going to choose 2 points because they are on the line of best fit. About there. They're on the line of best fit, so I can use those points. Planck's constant. One. Planck's constant equals the slope of the line, which equals y2 minus y1 over x2 minus x1. Most people can do this. Y2 is 1.8 to 9.7. 1.8 to 9.7, and x1 is 0.33, isn't it? Sorry, y2 minus y1. Have I got that right? Hang on. Yeah, 1.8 to 0.33. 0.33 over x2, which is 9.7. I'm going to put brackets around it. That's going to be clear y in a second. 9.7 minus 6. Don't forget to put the times 10 to the 14. Okay. Somebody want to do that calculation for me, please? Didn't I do that? Didn't I use 2 points on the... Oh, okay. Yes, you could do. Yes, absolutely. Yes. So instead of using these 2 points, which are taken from my measurements, okay, even though they're on the line of best fit, yes, you could. You could use the x-axis, so 0, 4 point whatever, and minus 2 point something, 0. Yes, definitely. That value comes out at 1, hang on, 2 part A, Planck's constant, slope, 4 by 10 to the minus 15. Did anybody calculate that and find that? Yes, that's the number that you got. That's not Planck's constant, is it? What's wrong? H on E equals 4 by 10 to the 15. Minus 15. Sorry. Now, if I multiply that by E, I get H. H equals, or Planck's constant rather, 4.0 by 10 to the minus 15 multiplied by 1.6 by 10 to the minus 19 equals 6.6. Yeah, it should be. We'll say it is anyway, by 10 to the minus 34. At least you should get the order right. If you get 6.62, 6.64, it's okay. It's close enough. Well, that's the best, of course. But remember, we're using a simulator. Theoretically, the simulator is good. Where do I find... The next question says the work function of the metal. I heard somebody maybe say it. Yeah, it's the y-intercept, isn't it? W equals y-intercept, which equals, what did we say? 0.5, 1, 1.5, 1 point, 1 point, what was that? That was 1.5, wasn't it? That's 2, 1.75, 1.82. Wait, 1.81 EV, I'll say, by my graph. The next part says the threshold frequency of the metal. How do you find that? Yeah, it's the x-intercept, isn't it? That's it. Threshold frequency, F naught, F sub naught equals, what is it? 4.9 by 10 to the 14 hertz. Last question says the maximum kinetic energy of electrons emitted by light of frequency 8 by 10 to the 14. How do you work that out? You 5, 6, 7, 8, line it up. It's that point there, which lines up with 1.3. So part D, is it, equals 1.3 electron volts. If you wanted to change that to joules, they said put your answer in joules. How would you do that? Yeah, multiply by the electron charge and you get that value in joules. One more example and then you guys are off the hook. Yes. Oh. What's this say? Tablet battery is low. Okay. About to run out of power. That's it. Oops. The work function of copper is 4.7 eV. Determine the maximum kinetic energy of the emitted electrons if the metal is irradiated with ultraviolet light of wavelength 2 by 10 to the minus 7 meters. See how you go. Last question. This one isn't so long. Work function W equals 4.7 eV. They want us to find the maximum kinetic energy. So we're going to be using this formula, aren't we? We know that kinetic energy maximum is equal to H Planck's constant multiplied by the frequency minus the work function of the metal. So I need to know the work function in joules, and I need to calculate the frequency from the wavelength. So work function is equal to 4.7 times 1.6 by 10 to the minus 19 joules, which equals, what was it? Has anybody calculated that number? 7.52 by 10 to the minus 19. Oh, we did that number earlier. And F is equal to C on lambda. 3 by 10 to the 8 over 2.0 by 10 to the minus 7, which equals Did anybody calculate that one? 1.25? 1.5. Thank you. 10 to the 15. Sounds good. Sounds like these sound like good numbers. Okay, then all we have to do is, yes, 6.63 by 10 to the minus 34 times frequency, which is 1.5 by 10 to the 15 minus W 7.52 by 10 to the minus 19, and we should get 2.43 by 10 to the minus 19 joules. Maximum kinetic energy the emitted electrons. That's it for today. Lesson time.